Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked in the GATE Physics paper 2021. This is a multiple select question, that is MSQ, having 1 mark. The topic of the question is solid state physics. Specifically, this question was asked from the chapter Reciprocal Lattice. The question is, a two-dimensional square lattice has lattice constant small a. K represents the wave vector in reciprocal space. The coordinates kx, ky of reciprocal space where band gap or band gaps can occur, those are: option A is at 0, 0, that is at origin. Option B, plus minus pi by a, plus minus pi by a. Option C, plus minus pi by a, plus minus pi by 1.3a. And the last option, option D, plus minus pi by 3a, plus minus pi by e. So as this is a MSQ type question, so it is possible to have multiple options correct for this question. So let us see how to solve this problem. Before going to the main part of the solution, let us discuss very briefly about the Brillouin zone and how can we construct the Brillouin zone for a 2D square lattice having lattice constant small a. So what is Brillouin zone? Brillouin zone is the locus of all those k values or k points in the reciprocal space or k space of a crystal structure which are Bragg's reflected. So you can see here a schematic which basically describing the first and second Brillouin zone of a 2D square lattice having lattice constant small a. So let us understand how can we describe the first and second Brillouin zone for this from this schematic. So you can see here a square region which is shaded by the horizontal lines, and origin is at the middle of the square. So this square region is basically bounded by 4 straight lines. Those are kx equals to minus pi by a, kx equals to pi by a, ky equals to pi by a, and ky equals to minus pi by a. So this square region is the first Brillouin zone for the 2D square lattice in the K space, that is kx, ky plane. And these 4 sides, which are basically the 4 straight lines, these are the first Brillouin zone boundaries. So this is how we can describe the first Brillouin zone boundary for a 2D square lattice. Now what about the second Brillouin zone? So to construct the second Brillouin zone, basically we need these 4 straight lines kx minus ky equals to minus 2 pi by a, kx minus ky equals to 2 pi by a, kx plus ky equals to minus 2 pi by a, and kx plus ky equals to 2 pi by a. So these 4 lines, straight lines, will basically construct the second Brillouin zone for the 2D square lattice. So the area enclosed by these 4 lines, excluding this first Brillouin zone area, will give the second Brillouin zone. So basically these 4 region shaded with vertical lines will basically give the second Brillouin zone of the 2D square lattice, and the boundary lines are the second Brillouin zone boundaries. Now let us see how can we basically construct these Brillouin zone and Brillouin zone boundaries from the vector form of the Bragg's law. So let us see. In the previous slide, we have already seen the first and second Brillouin zone for the 2D square lattice having lattice constant small e. Now we'll understand how can we construct the Brillouin zones and Brillouin zone boundaries from the mathematical equation. For this, we need primitive translation vectors for the 2D square lattice. Those are a vector equals to a I cap, that is along x cap direction, and B vector equals to aj cap along y cap direction. The corresponding translation vectors in the reciprocal space, that is in the K space, will be A star vector equals to 2 pi by A along I cap direction and B star vector equals to 2 pi by A along J cap direction. So by knowing these A star and B star vectors in the K space, we can construct the reciprocal lattice vector, that is G vector equals to 2 pi by A times H I cap plus K J cap, where H and K are the integers. And the wave vector in the K space, that is K vector, is basically Kx I cap plus Ky j cap. So the vector form of the Bragg's law is given by this equation. This equation is 2 times K vector dot product with G vector plus G square equals to 0. From the earlier slides, we have already seen this K vector is the wave vector in the Kx Ky plane. So this K vector will be Kx I cap plus Ky j cap. And G vector basically denotes the reciprocal lattice vector for the crystal structure, two-dimensional square lattice. So this G vector for the two-dimensional square lattice will be 2 pi by A times H I cap plus K j cap. Now we'll put all the expressions for the K vector and G vector in this equation. Then we'll get 4 pi by A times Kx I cap plus Ky j cap dot product with H I cap plus K j cap plus 4 pi square by A square times H square plus K square equals to 0. So this second term is coming for the G square term here, and this 2 times K dot G vector is giving this first term in this equation. Now we'll perform the dot product here. It will give the Kx I cap dot product with H I cap will give the Hkx, but this Kx I cap dot product with Kj cap here will give the 0 because I and j are the unit vectors orthogonal to each other. Similarly, Ky j cap dot product with H I cap will give 0, but the Ky j cap dot product with Kj cap will give Ky. So after some rearrangements, we'll get this equation Hkx plus Kky equals to minus pi by A times A square plus K square. Here H and K are the integers. So what does this equation tells us? So this equation basically telling us about the location or locus of the K points which are Bragg reflected. Now H and K are the integers. So first we'll put H equals to plus minus 1 and K equals to 0. So this will basically lead to Kx equals to plus minus pi by A and Ky can be any arbitrary value. Similarly, we can put H equals to 0 here and K equals to plus minus 1. This will basically lead to Ky equals to plus minus A and Kx can be any arbitrary value. So from this combined of these conditions, we can get Kx equals to plus minus pi by A and Ky equals to plus minus pi by A. So these are basically constructing the boundaries for the first Brillouin zones. So these 4 lines will give the first Brillouin zone boundaries here. That we have already seen in the first schematic diagram. So till now we have already seen how can we construct the first Brillouin zone boundaries for the two-dimensional square lattice from the vector form of the Bragg's law. And those 4 lines are Kx equals to plus minus pi by A and Ky equals to plus minus pi by A. So these 4 lines are the boundaries for the first Brillouin zone that we have constructed mathematically already. Now we will consider the second possible integer values for the H and K. So those are H equals to plus minus 1 and K equals to plus minus 1. So if we put this H and K value in the equation of the locus of all K points, those are Bragg's reflected, then this will get another 4 lines which will basically give the boundaries for the second Brillouin zone in the 2D square lattice. So then we will get these 4 lines kx minus ky equals to minus 2 pi by a, kx minus ky equals to 2 pi by a, kx plus ky equals to minus 2 pi by a, and kx plus ky equals to 2 pi by a. These 4 lines will basically construct the second Brillouin zone boundaries in the kx and ky plane. So now we have the idea how can we construct the Brillouin zones for the 2D square lattice, and how does it look for the first Brillouin zone boundary and second Brillouin zone boundary. Now whenever an electron strikes the Brillouin zone boundaries, its group velocity, which is given by Vg equals to 1 by h cut del E del k, where E is the energy and k is the wave vector, that becomes 0 as at the Brillouin zone boundaries. What does it mean? It leads to basically the generation of energy band gap or energy gap at the Brillouin zone boundaries. Hence, all points lying on Brillouin zone boundaries will give rise to energy band gap in the crystal structure. Now, all the k points of first Brillouin zone boundary lies on the 4 lines. Those are kx equals to plus minus pi by a. These two lines are shown here, kx equals to minus pi by a here, and kx equals to pi by a, and ky equals to plus minus pi by a. Those two lines are here, ky equals to pi by a and ky equals to minus pi by a. So these 4 lines will basically construct the boundary of the first Brillouin zone, and at all the points on this boundary we'll get the energy band gap. Now there are 4 points given in the options. First option was 0, 0, that is the origin. So the origin is not lying on the boundary, so it is not possible to have the energy band gap at the origin. So this option can be eliminated. Now for the other 3 options, so we will just discuss one by one. First, second option was plus minus pi by a, comma plus minus pi by a. So these are basically 4 points. These 4 points are here at the corner of the square. So these are lying on the boundary of the first Brillouin zone. So this is the possible answer 1. So then the third option, plus minus pi by a, comma plus minus pi by 1.3a, these points are lying somewhere like here, here, or here and here. So these 4 points will lie on the boundaries. So this is also possible answer. And for the last option D, plus minus pi by 3a, comma plus minus pi by a, these 4 points will basically lie somewhere like here, here, or here, or here. So these 4 points will lie on the boundary of the first Brillouin zone. So this is also the possible answer. So effectively we are getting option B, C and D are correct for this question. We have already discussed in the earlier slides about the Brillouin zone. Then how to construct the Brillouin zone for a 2-dimensional square lattice that has lattice constant small a. Then we have discussed how the energy gap or band gap can arise at the zone boundary, that is at the boundary of first Brillouin zone, second Brillouin zone, or so on. And after that we solved this problem, and we found that the option B, C and D, that is at plus minus pi by a, comma plus minus pi by a, plus minus pi by a, comma plus minus pi by 1.3a, and plus minus pi by 3a, comma plus minus pi by a. So these 3 options B, C and D, at this point in K space the band gaps can occur. So these 3 options are the correct answer for this question. This question is from the GATE Physics paper 2021. This is a numerical answer type, that is NAT, having 2 marks. The topic of the question is solid state physics. Specifically, this question is from the chapter Magnetic Properties of Material. The question is, consider an atomic gas with number density n equals to 10 to the power 20 per meter cube in the ground state of the atom at temperature 300 Kelvin. The valence electronic configuration of atoms is F7. So this means the last partially filled orbital is F, and that orbital, F orbital, contains 7 electrons. The paramagnetic susceptibility of the gas chi equals to m times 10 to the power minus 11. The value of m rounded off to 2 decimal places is, so basically you have to find the value of m which should be rounded off to 2 decimal places. There are some important informations are given which is required to solve this problem. The informations are: magnetic permeability of free space mu naught equals to 4 pi times 10 to the power minus 7 Henry per meter. The Bohr magneton mu b value is 9.274 times 10 to the power minus 24 ampere meter square. So basically the Bohr magneton is the magnetic moment of the elementary charge, that is electron, which occurs due to the spin or orbital angular momentum of that electron. And Boltzmann constant Kb equals to 1.3807 times 10 to the power minus 23 joule per Kelvin. So these informations we have to use to solve this question. So let us see how to solve this problem. According to the quantum theory of paramagnetism, we have the paramagnetic susceptibility chi equals to mu naught times n times mu j square by 3 kBt. Here mu naught is the magnetic permeability of free space. Kb is the Boltzmann constant, n is the number density of atoms, mu j is the effective magnetic moment of atoms. Here mu j can be written as Gj times root over j times j plus 1 times mu b, where Gj is the Landis G factor, J is given by L plus S, which is total angular momentum of the atom, and in our question some informations are given already. N, that is the number density of atoms, is 10 to the power 20 per meter cube. Temperature of the system T equals to 300 Kelvin. The valence electronic configuration of the atoms is F7. According to our question, the atomic system has the valence electronic state F7. Now we'll see how can we accommodate the 7 electrons in the F subshell or F orbital. For F orbital or the F subshell, we know the L value, that is the orbital angular quantum number or the azimuthal quantum number, L equals to 3. For L equals to 3, we know we can have ml values from plus 3 to minus 3. So we'll have 7 ml values. So basically there are 7 electronic states in the F subshell or the F orbital. So for these 7 electronic states, we can accommodate the 7 electrons in such a way each electronic state will contain one single electron. So as you can see from this configuration of the F orbital, the ml equals to plus 3 will contain one upspin electron, and correspondingly all the other electronic states will contain a single electron with upspin. So for this configuration of the electrons in the F orbital, we will have total spin quantum number S equals to summation over all ms, that is the spin quantum number of the electron, that will be 7 times 1 by 2, that is 7 by 2. But total orbital quantum number L equals to summation over all magnetic quantum number ml. So as this is half filled, so the summation of all ML will be 0 here. Now total angular momentum quantum number J equals to L plus S. So here S value is 7 by 2 and L value is 0 for this system. So this summation will give J equals to 7 by 2. So for the atomic system or atomic gas, the total angular quantum number J equals to 7 by 2. Now the spectroscopic term for the atoms with valence electronic configuration F7 is given by 8s7 by 2. This spectroscopic term is generally represented in the form of 2s plus 1 Lj. In our case, the S value is 7 by 2. So this 2s plus 1 will give 8. Now the L value, that is the total orbital angular quantum number, L equals to 0. For this we are having here x, and the total angular momentum quantum number is 7 by 2, that is J equals to 7 by 2. So we'll have here 7 by 2. Now the Landesi factor is defined as Gj equals to 1 plus J into J plus 1 plus S times S plus 1 minus L times L plus 1 divided by 2J multiplied with J plus 1. So we have for our system S equals to 7 by 2, L equals to 0 and J equals to 7 by 2. So we'll put this S value, L value and J value in this formula of the Landesi factor. So we'll have the Landesi factor Gj equals to 1 plus 7 by 2 times 7 by 2 plus 1 plus 7 by 2 times 7 by 2 plus 1 minus 0, as here L equals to 0, divided by 2j times j plus 1, here j equals to 7 by 2. So we will have here in the denominator 2 times 7 by 2 times 7 by 2 plus 1. Now if we calculate this, we will get the Landesi factor for our system Gj equals to 2. Now we will calculate the effective magnetic moment per atom. The effective magnetic moment per atom is given by mu j, which is given by this formula, that is mu j equals to Gj times root over j times j plus 1 times mu b. Here Gj is the Landesi factor of the atom, J is the total angular momentum quantum number of the system, mu b is the Bohr magneton. We have already calculated the Gj and J value for our system. The Landesi factor Gj is 2 as per our calculation, and J value is the 7 by 2. So we'll put the values here. So we'll get 2 times root over 7 by 2 times 7 by 2 plus 1 and mu b. Now mu b is given already in the question, that is 9.274 times 10 to the power minus 24 amps meter square. So if we calculate this, then we will get mu j equals to root over 63 for this two term, 2 times root over 7 by 2 times 7 by 2 plus 1 times mu b. So mu b will put the value. So we'll get root over 63 times 9.274 times 10 to the power minus 24 amps meter square. Now the parametric susceptibility from the quantum theory is given by chi para equals to mu naught in mu j square divided by 3 kBt. So we have already calculated the mu j value, it is given here, and from the question we know mu naught value, in value, and the temperature of the system is 300 Kelvin, and Kb is the Boltzmann constant that we already know from the question. So we'll put all the values here, then we will get chi para equals to 4 pi times 10 to the power minus 7, that is the mu naught value. In value is 10 to the power 20, and mu j squared is the this root over 63 times 9.274 times 10 to the power minus 24 whole square divided by 3 kb. K value is 1.3807 times 10 to the power minus 23 times temperature value of the system, that is 300 Kelvin. So after putting this, if we calculate this, we will get chi para equals to approximately 5.48 times 10 to the power minus 11. So we have to find the value of m, which is actually here 5.48. So the value of the m as it has been asked in the question, that is 5.48. So we have already solved this problem in details, and we found that the value of m in the paramagnetic susceptibility of the gas chi equals to m times 10 to the minus 11 is 5.48, which is rounded off to 2 decimal places. This question is from the GATE Physics paper 2021. This is a MCQ type question of 2 marks. The topic of the question is solid state physics. Specifically, this question was asked from the chapter Magnetic Properties of Material. According to the question, as shown in the figure, inverse magnetic susceptibility, that is 1 by chi, is plotted as a function of temperature T for 3 different materials in paramagnetic states. So this plot for 1 by chi versus T is given for 3 different kind of magnetic materials. So this is the plot for the first material, this second plot is for the second material, and third plot is for the third material. So there are mainly 3 types of magnetic materials. They are paramagnetic, ferromagnetic and antiferromagnetic. So we have to identify which plot corresponds to which material. So here some informations are given. Curie temperature for ferromagnetic material is Tc, Néel temperature for antiferromagnetic material is Tn. Then we have to choose the correct statement from the following. Option A is material 1 is antiferromagnetic for T less than Néel temperature Tn, 2 is paramagnetic, and 3 is ferromagnetic for T less than Curie temperature, that is Tc. Option B is material 1 is paramagnetic, material 2 is antiferromagnetic at T less than Tn, and material 3 is ferromagnetic for T less than Tc. Option C is material 1 is ferromagnetic for T less than Tc, material 2 is antiferromagnetic for T less than Tn, and material 3 is paramagnetic. And the last option, option D, is material 1 is ferromagnetic for T less than Tc, material 2 is paramagnetic, and material 3 is antiferromagnetic for T less than Tn. So we have to identify properly which material corresponds to which curve. So let us see how to solve this problem. For paramagnetic materials, from the quantum theory of paramagnetism, we know the paramagnetic susceptibility chi para is given by mu naught times n times mu effective whole square divided by 3 kVt. Here mu naught is the magnetic permeability in vacuum, n is the number density of the atoms in the system, mu effective is the magnetic moment per atom, and Kb is the Boltzmann constant, and T is the temperature of the system. So basically the susceptibility of the paramagnetic material is proportional to 1 by T. So it is inversely proportional to temperature. So at a particular temperature, all the terms except from the temperature T will be constant. So we can represent this chi para as A by T, where A is the constant. So 1 by chi para will be 1 by A times T. So it is proportional to temperature. So if we just plot this 1 by chi para versus temperature, then we'll get a straight line and that will intersect at the origin. So our second material is the paramagnetic material from our question. Now for the ferromagnetic materials, we know the susceptibility of the ferromagnetic material is given by Curie-Weiss law for T greater than Tc, that is in the paramagnetic state. So the chi ferro equals to B by T minus Tc. B is the constant here, so 1 by chi ferro will be 1 by B times T minus Tc. So 1 by chi ferro is proportional to T minus Tc. So for a ferromagnetic material, the chi ferro is proportional to 1 by T minus Tc for T greater than Tc, that is in the paramagnetic state. So if we plot the chi versus t for a ferromagnetic material at t greater than Tc, then the curve will look like this. Now we'll plot the 1 by chi ferro versus temperature. So 1 by chi ferro is proportional to T minus Tc, so it will be a straight line and it will intersect the 1 by chi ferro axis at a negative value, that is minus 1 by b times Tc, and this curve will intersect the t-axis at the Curie temperature, that is Tc. So it looks like the curve for third material according to the question. So the third material will be the ferromagnetic material. Then for antiferromagnetic material, the susceptibility for antiferromagnetic material is given by C by T plus Tn. Here C is the constant and Tn is known as Neel temperature. So it is a phase transition temperature. So basically for temperature less than Tn, the material will be in the antiferromagnetic state, but for T greater than Tn, it will have a phase transition and it will go into the paramagnetic state. For the antiferromagnetic material, 1 by the antiferromagnetic susceptibility is given by T plus Tn divided by a constant C, and it is applicable for temperature greater than Neel temperature Tn. So our 1 by chi Nt is proportional to T plus Tn. So if we plot this for T greater than Tn, then it will be a straight line, and if we extend this straight line by this dotted version, then this will intersect the t-axis at minus Tn, and it will intersect the 1 by chi Nt axis at a positive value. So it seems that our first material is antiferromagnetic. Now we have plotted the 1 by susceptibility versus temperature for all the three materials. Those are paramagnetic, antiferromagnetic and ferromagnetic. So this plot shows the all three curves. So from here we can conclude the graph 1 or the curve 1 corresponds to the antiferromagnetic material for T less than Tn, and the graph 2 corresponds to the paramagnetic material, and the graph 3 it corresponds to the ferromagnetic material for T less than Tc. So according to the options, our option A is the correct answer for our question. So from the solution of this question, we found that the option A is correct for this question, which means this plot 1 or curve 1 corresponds to antiferromagnetic for T less than Tn, and this curve 2 is basically for paramagnetic material, and this curve 3 corresponds to ferromagnetic at T less than Tc.